quantity of heat absorbed. So when a system absorbs heat, its temperature will increase. And it increases by amount we call delta T, the change in temperature. The change in temperature is directly proportional to the amount of heat that was absorbed. And so if it's proportional, there must be a proportionality constant. And that constant is known as the heat capacity. And it is abbreviated with a capital C. Now, the abbreviation here, capital C, depending on the author or the field of study, you'll sometimes see different letters used. Sometimes you'll see a lowercase c or even an S. But we're going to use capital C. The units on that are joules per degree Celsius or joules per Kelvin. So Q is equal to the proportionality constant times the change in temperature. And if we look at the units and how those work out, the units on C are joules per degree Celsius, and the change in temperature in degrees Celsius, we see that cancels out, and we have Q with the unit joule, which is appropriate because it's an energy unit. So what is the physical meaning of that proportionality constant? That heat capacity is the amount of heat energy needed to change the temperature of a system by 1 degree Celsius. Now, what gets a little confusing is Kelvin and Celsius here. This is a change in temperature. The Celsius and Kelvin units are the same size. They're just offset as to where 0 is. So when you're subtracting them, Kelvin and Celsius will give you the same result. And if you want me to show that to you, we can do it later. But we're behind in lecture, so I don't want to take too much time on that. The larger the heat capacity of the object, the smaller the temperature rise. The heat capacity is the amount of energy needed to change the temperature 1 degree. So if it takes twice as much energy to change the temperature by 1 degree, then if the amount of energy is the same, we're going to see a different change in temperature. The heat capacity also depends on the amount of matter. And usually we measure this as mass. So we say that heat capacity is an extensive property. It depends on the amount of stuff you have. If you're trying to boil water for spaghetti, and you're making a small pot of water just for 1 serving of spaghetti, or you've got a big stock pot like I have to cook for my family, because we normally cook 2 pounds of spaghetti for a meal. My children are animals. Which one is going to take more energy to heat up? The little pot or the big pot? The big pot, of course. That makes sense to us. Larger amount of water, larger mass of water, it's going to require more energy to get the same change in temperature. So heat capacity isn't that useful of a property because it depends on the amount of substance. So what we often use is specific heat capacity. This is an intrinsic property, does not depend on the amount of substance. And so the specific heat capacity is going to have units like joules per gram degree Celsius. And so that's going to take out that mass effect. The heat capacity also depends on the type of material. Some materials heat up very quickly, and some materials heat up very slowly because it takes more energy to change their temperature. So, I got ahead of myself again. Specific heat capacity, C sub S, amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. So now we're specifying the amount. The units are going to be joules per gram degree Celsius, or they could be joules per gram Kelvin. Sometimes we'll use a molar heat capacity, and here we're defining the amount of substance in moles instead of grams. So that'll give you joules per mole degree Celsius. Both of these are intensive properties. They do not depend on the amount of substance or the size of the sample. So here's the equation. Q, the heat, is in joules. That is equal to the mass of the object in grams times its specific heat capacity, units of joules per gram degree Celsius, times the change in temperature in degrees Celsius. Here's a table from your textbook giving specific heat capacities of several different substances. We see these metals: lead, gold, silver, copper, iron, aluminum. These all have relatively low, less than 1 specific heat capacities. And then look at water, 4.18. Water has an unusually high specific heat capacity. The molar heat capacity is the energy needed, or the heat needed, to raise the temperature of 1 mole instead of 1 gram. So this is an important little equation. Q equals MC delta T, technically with an S there. I call that the Q equals MCAT because that delta kind of looks like a capital A. So Q equals MC delta T, or Q equals MCAT. You can actually figure that out just looking at the units, because if you take the specific heat capacity, the units will always be given in the table. You can see that you need to multiply by grams and multiply by degrees Celsius in order to get joules. The high specific heat capacity of water is actually very significant for life on Earth. Water can absorb a tremendous amount of heat energy and only have a small increase in temperature. So a lot of people in the Central Valley like to go to the central coast of California in the summer because it's stinking hot here, and you can go to the beach there and sit in cloudy weather with gale-forced winds blowing on you, and it's like 70 degrees maybe, and you're freezing to death. And this is something that people in the rest of the country don't understand, that a lot of Californians go to the beach to get cold, right? We go to escape the heat. Why is it colder there on the coast? It's because of the ocean. The ocean is this huge body of water. The sun comes down and bakes the valley, this summer especially. It's been just bone dry here. And the ground, the earth, has a low specific heat capacity. The sun hits the ground, it warms up, the air warms up. But when the sun hits water, the water does not change in temperature very much. And so my son had the opportunity to spend the summer in San Francisco. And the temperature there is relatively constant between winter and summer. It's almost colder in the summer there than it is in the winter because it's surrounded by water. And so during the day, as the sun's heat comes down, the bay and the ocean absorb all this energy. The temperature goes up only slightly. At night, the temperature doesn't change much because when the sun goes down and the air is cooler, then the water slowly radiates heat back into the atmosphere, and it moderates the temperature. Here, it's not unusual. Here in Fresno, it's not unusual to have a 40-degree temperature change between the high of the afternoon and the low of the evening, right? It happens, and it's bizarre, and it's because of this low humidity we have and the very little amount of water. The reason that we use water in cooling systems like your radiator, it can absorb a lot of heat without changing temperature much, and so it's more effective at cooling things than, say, air. Another word problem with way too many words. Okay. To determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds that it has a mass of 4.7 grams. Well, as long as we're reading through this, let's just write some of these things down. That was pretty clear. mass equals 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, what letter do we use to represent heat? Q. So it's absorbing, is that positive or negative? Positive. So 57.2 joules. The temperature of the rock rises from 25 degrees Celsius to 47 degrees Celsius. So we have two temperatures there. We have a temperature that's 25, and we have a temperature that is 47. So it went from 25, so that's initial, and the final is 47. Find the specific heat capacity of the substance composing the rock. Determine whether the value is consistent with the rock being gold. Specific heat capacity is an intrinsic property, just like density. It doesn't depend on the amount of substance, it depends on what the substance is. So it can be used to identify. It'd probably be simpler to find the density of the rock, but that's not what she did. So our equation is Q equals mc delta T. We have Q, we have M, we have the information we need to get delta T. It's final minus initial. And we're asked to find C. So we're just going to rearrange the equation. We want to move these to the other side. So our specific heat capacity that we're looking for is going to be equal to Q divided by the mass times the change in temperature. The change in temperature is always final minus initial. T final minus T initial. And so the final temperature is 47, and the initial is 25. So I think that's 22 degrees Celsius. So now we have all the values we need. We've got 57.2 joules, and we have a mass of 4.7 grams, and a temperature change of 22 degrees Celsius. Writing large today, that would have two sig figs, so 0.55 joules per gram degree Celsius. Well, can we tell just by looking at that number? We need to compare it to something. You have a question? It has to be in Celsius or it can be in Kelvin. Because if we convert these temperatures to Kelvin, let's look at that real quick. Because that's one of those things that there's questions on labs and stuff that trip people up because of this. So if we convert 25 degrees Celsius, well, I need to leave the units off, to Kelvin, we add 273.15, right? And if we convert 47 to Celsius, we add 273.15. When we subtract these two numbers, the 273.15 that we added to both of them goes away, right? So if it's Kelvin, you just find the difference and you're good. If it's Celsius, you find the difference and it's fine. Okay? So 0.55, we need to go look up what is the specific heat capacity of gold. Well, I'll be back here. Gold is 0.128. Is that close to 0.55? Not with the way these are varying, no. So, 0.55 doesn't match up with anything exactly, but it's probably closest to iron. It's probably just painted iron or something like that. Any questions about that problem? So when two objects at different temperatures are in contact, heat flows from the high temperature to the low, and it goes until it gets to some middle final temperature. The energy lost by the hot thing is equal to the energy gained by the cold material. So if we have a block of metal at 55 degrees Celsius and we stick it in some water that's at 25 degrees Celsius, the metal is going to lose heat energy, the water is going to gain heat energy. The energy lost by the metal is equal to the energy gained by the water. The negative sign is in here because one is a positive and one is a negative, but the number's the same. So the exact temperature change that you end up with is going to depend on the mass of the water. It's also going to depend on the mass of the piece of metal and what the specific heat capacity of the metal is. If the chunk of metal is larger, the water's going to warm up more than if it was smaller. That makes sense. If this is something with a high specific heat, then the water's going to change more than this if this is something with a low specific heat. So Q for the metal is equal to the mass of the metal, the specific heat capacity of the metal, the change in temperature of the metal. Q for the water is, and here we're dealing with negative because it's opposite in sign. We've got mass of the water, specific heat of the water, change in temperature of the water. Does that make sense? So let's do a problem like this. A block of copper of unknown mass has an initial temperature of 65.4. Let's write all this down. I'm going to use orange for the copper stuff. So initial temperature of the copper, 65.4 degrees Celsius. It's immersed in a beaker containing a mass of water. The mass of water is 95.7 grams. The water is initially at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2. Is that the mass of the water or the mass of the mass? Is that the temperature of the water or the temperature of the copper? Both. Very good. They come to the same final temperature. So the final temperature of the water is 24.2 degrees. The final temperature of the copper is also 24.2 degrees. And what we're asked is, what's the mass of the copper? We do not have all the information that we need. We also need specific heat capacities for both of these substances. So let's go back to that table and look up the specific heat capacity of copper. It's 0.385, and we also need water is 4.1. So 0.385, 0.385 joules per gram degrees Celsius. And for the water, the specific heat capacity is 4.18 joules per gram degrees Celsius. The copper is losing energy. The water is gaining that same amount of energy. So Q for the copper is equal to negative Q for the water. You could put the negative sign in front of the copper. It doesn't matter. They're just going to come up being opposite. So Q for the water is MC delta T. And Q for the copper is also MC delta T, but it's its own MC delta T. MC delta T. What's lost by the copper has to be gained by the water. What are we trying to find here? The mass of the copper. So instead of plugging numbers in, I think it's best to rearrange when it's still manageable with just these letters. So I need to divide by specific heat capacity of the copper and specific heat capacity, the temperature of the change of the copper. So these cancel out. I don't have a lot of space on this slide, so I'm going to clean this up. That's the mass. Everybody okay with that? Okay, so the mass is going to equal, now we're going to put numbers in. We can't forget that negative sign. You might think, well, how can the mass be negative? Just wait, it's not going to be. The mass of the water was 95.7 grams. The specific heat capacity of the water was 4.18 joules per gram degree Celsius. What is delta T for the water? 1.5. It's 24.2 minus 22.7. So 1.5 degrees Celsius? Am I? No. 1.5. Ah, squeezed in there. I'm going to write this up at the top because it might be a little confusing. Delta T for the water is the final minus the initial, 24.2 minus 22.7. So that's 1.5. What is delta T for the copper? It's the final minus the initial. The final is 24.2. The initial is 65.4. That's going to be a negative number. Because if one thing warms up, the other thing's cooling down. One change is positive, one change is negative. 24.2 minus 65.4 minus 41.2. Okay, so I got the numerator in there. And then we've got the specific heat capacity of the copper. Sorry, this is such a mess. That's a 0. And negative 41.2 degrees Celsius. So I've got negative 95.7 times 4.18 times 1.5 divided by 0.385 divided by negative 41.2. And I come up with a positive number, 37.8. Bless you. 37.8 grams. Any questions? The math here isn't hard. There's just a lot of numbers that look similar, and you got to keep track what's what. It's nice here because I can use colors. If we don't use colors, then we use subscripts. You know, maybe W for water and C for copper or something like that. So we've been talking about Q, the heat. We also need to talk about work. There are different forms of work. One is known as pressure volume work. This is work caused by a volume change against an external pressure. There is atmospheric pressure, and so if you expand something, you're working against an external pressure. So the change in volume is positive because it's getting larger, but the system is doing work on the surroundings, and that means that the work itself is negative. W for the gas is negative, and so we end up with the work is equal to negative pressure times the change in volume. The change in volume is positive. The pressure, of course, is positive. But the way we've defined it, W has to be negative, and so we just have a negative sign in front of that. Here's the illustration. This gas expanding. The volume is increasing. It's doing work against atmospheric pressure. Now, if we have a pressure and a volume, what kind of units are we going to end up with? Things get kind of funky there. Let's look at that. Well, pressure, if pressure is in atmospheres and change in volume is in liters, we end up with atmosphere liters. How is that a unit of energy? Well, through all those crazy units like kilogram, meter squared per second squared, and things like that. 1 atmosphere times liter is equal to 101.3 joules. And so this is an important little conversion factor that is easily forgotten and can cause a lot of confusion. So you need to use that periodically. So let's do an example. A cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. If the initial volume is 0.485 liters, the final volume is 1.245 liters. How much work in joules is done? Well, let's identify these different things. 1.58, that must be a pressure, right? That's the pressure. Pressure is 1.58 atmospheres. Initial volume is 0.485 liters. No, that's backwards. Liters. Oh, that's ugly. There we go. Final volume, 1.245 liters. I get joules on my brain. Asking for work. Work equals negative P delta V. We've got the pressure, we need delta V. Delta always means final minus initial. So this is the final volume minus the initial volume. 1.245 liters minus 0.485 liters. .76. Now what's wrong with how I wrote that? 0.76. I need a 0 at the end. Here I'm subtracting, and there's uncertainty in the third decimal place, and in the third decimal place, the 5 minus 5 is 0, but that is a significant digit, and so I can't just omit that. My calculator's not going to show it to me, but I have to remember it's important and it's there. So there's our change in volume. So W equals negative the pressure, 1.58 atmospheres, times the change in volume, 0.760 liters. So that comes out to be negative 1.2008 atmosphere liters. Is that the same as joules? No. There's a relationship 101.3 joules per atmosphere liter. I'm going to move this guy over. So we need to convert. 101.3 joules is equal to 1 atmosphere liter. So then I take that result times 101.3. For 3 significant figures, I'm going to end up with minus 122 joules. Any questions? Could the change in volume be negative? Can you have a negative change in volume? You can. That means that it got smaller. If delta V was negative, then the work would end up being positive, because that would mean that the system did work, the surroundings did work on the system. You can't have negative volume, but you can have negative change in volume. You can't have negative pressure, though. It's not possible.